Welcome back to the FAST lecture series. Today, as we start talking about chemical reactions, we're going to take a little bit of a look at a foundational principle of how chemical reactions actually work. And that foundational principle is the law of conservation of matter. Now, really all this is saying is that in chemical reactions, you can't create or destroy matter that wasn't already there. And if that sounds really familiar to you, you're probably right, because this is actually really just the same thing as the first law of thermodynamics, which you've seen a lot, right? So interestingly enough, this law applies to many things. So for example, if we take a look at a piece of matter, we'll just say it's this rock. It's a beautiful rock. If you took this rock and then wanted to just blink it out of existence, if you were a wizard, you can't really do that, right? So this is actually impossible according to the law of conservation of matter. You can't just blink matter out of existence. Likewise, you couldn't do this in reverse, where you have nothing and then suddenly you make a rock. Why you would want to make a rock? I don't know, but you couldn't do it even if you wanted to. Now, the question is, how does the law of conservation of matter, or this idea of retaining all matter, apply to chemical reactions? Well, let's take a look at this one down here. And this is one that we will probably see in class, and that you may actually do, where you have some solid iron that's combining with an aqueous copper sulfate, and that is going to react and turn into iron sulfate and copper. So you can kind of see that these switched places. It's called a single replacement. We'll talk about that later. But how does this apply to the law of conservation of matter? Well, really what we want to find out then is that if this reaction is true and it adheres to the law of conservation of matter, we should have the same amounts of matter on this side as we do on this side of the equation. Now, I like to do this by literally charting this out, and this might seem really tedious to you at the beginning, but as we get deeper into this, especially once we start balancing these equations, this little charting technique is actually going to come in handy. All right, so let's go ahead and count. So this is the pretty easy part. So we only have one iron on this side. We also only have one copper. We only have one sulfate. It's right there. And then we have an oxygen, but this subscript says that we have 4 of them. So that means that we're going to have 4 oxygens. So that's what we got on this side. Now if we take a look over here, we still only have one iron. Still only have one copper, it's just in a different place. Still only have one sulfur. And there's our oxygen, and there's that subscript of 4. So we have 4. And if we count all these up, we should see that they're equal. So we've got one over here for iron, one copper, one sulfate, and 4 oxygens and 4 oxygens. So this chemical reaction adheres to the law of conservation of matter, which means that it's a reaction that'll happen. Now, there will be some cases where you would see reactions that wouldn't happen. And a great example of this historically would be alchemists. So alchemists at one point, well actually for many years, they were tasked with creating gold out of everyday materials, and they would do a series of chemical reactions involving stuff like lead, and would try to turn that lead into gold. Now, we know that that is totally futile at this point, because if there was no gold in the reactants on this side of the equation, then there would never be gold over here. Because if it wasn't already present, then there's no way that you could just blink it into existence on the other side. So if you were thinking about becoming an alchemist and turning lead into gold in your spare time to get some extra cash, well, I hate to break it to you, probably not a great use of your time. And that is the end.